This is going to be just a quick lesson on rational and irrational numbers. We're going to begin by categorizing numbers into just their different names. We begin with natural numbers. A lot of you may be familiar with natural numbers as counting numbers. These are the numbers beginning with 1, and they just count up. 1, 2, 3, 4, 5, 6, whole numbers. No fraction pieces, nothing like that, but it starts at 1. So all of your natural numbers. Whole numbers are all natural numbers plus 0. So it's 0, 1, 2, 3, 4, 5, 6, 7, etc. Again, no fractional pieces involved, just whole numbers. Integers are the set of all whole numbers and their opposites. So it's all of these numbers and the negative values. So here is just a domain, a nice example set. You have -3, -2, -1, 0, 1, 2, 3. So you can see all of these opposites. Remember, 0 is its own opposite, and because the definition says the set of all whole numbers and their opposites, 0 is a whole number, so it falls under integers. But then we get to rational numbers. And rational numbers are numbers that can be written as fractions with integers for numerators and denominators. So we're going to get into the parts of wholes. So not only are we talking about all of our integers, but then all of the little pieces in between. Let's have a closer look at rational numbers. All rational numbers, like I said, can be written as a fraction. So here are just some quick examples of rational numbers, and I'm just going to show you that they do in fact have a fraction equivalent. 15, 15 over 1. Remember that a fraction is an unsimplified division problem. So 15 divided by 1 is 15, so 15 can be represented as a fraction by putting it over 1. -5 is -5 over 1. 75 hundredths can be written simplified as 3/4. We could also write it as 75 hundredths. It's still a fraction. -1 and 25 hundredths can be written in simplified form as -5/4. Remember, it's a numerator and a denominator. 2 and 1/4 is equivalent to just the numerator and denominator, the improper fraction, 9/4. 125 thousandths can be written as 1/8. We get to this sweet little guy here, 0.3 repeating. This is equivalent to the fraction 1/3. Let me just show you here. 1 divided by 3. I'm going to leave a little bit of room, fill in some zeros. 3 goes into 10 3 times, that's 9. 1 left over, bring down the 0. 3 goes into 10 3 times. That's 9 minus 1. Bring it down, and you can see that it's going to go on forever. This is 1 divided by 3, represented as the fraction 1/3. So 1/3 is a rational number. Just because it's this really long decimal, because it repeats and has that definitive pattern, it is rational. And then 1, of course, is a rational number, and we can represent 1 as a fraction by putting it over 1. But what about irrational numbers? Now, irrational numbers are numbers that cannot be written as a fraction. These are represented by decimals that continue with no sign of a pattern. They're irrational. They're really hard to handle. So think about something that's not fun to deal with. Maybe a person who's not fun to deal with can be considered irrational. Same concept here with a number that's not exactly fun to work with. The most popular example of an irrational number is pi. Pi, if you were to calculate it, now there are millions of digits of pi. Computers are working to calculate this all the time. But here, it's 3.141592653589793233846, etc. Like I said, there are millions of digits. This cannot be written as a numerator-denominator fraction because we don't know the end of the number. So it's not possible. It's very irrational, hard to handle. Difference between this and a rational number. Okay? The square root of 2 is also another common, popular, irrational number. And if you're unfamiliar with square roots, the square root of 2 means what number times itself would equal to. Here are some other common square roots just to kind of help you out here. The square root of 4 is 2 because 2 times 2, or 2 squared, equals the perfect square of 4. The square root of 9 is 3. The square root of 16 is 4. Because 3 times 3 is 9, 4 times 4 is 16. What number times itself equals 2? Well, that would be 1.414213 or 356, 237, etc., 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 etc. You can work and manipulate a decimal a bunch to get closer and closer and closer and closer to 2. But it just goes on and on and on and on and on and on and on. And to write that as a numerator and denominator is not possible. It's very irrational. Okay? That's an irrational number. So, there's one more point I want to make about rational and irrational numbers, and that is that rational numbers will always have an exact location on a number line, and then irrational numbers won't. So if I asked you to graph the set of numbers on the number line, well, these are all rational numbers. They're decimal numbers that come to an end, or they may have a repetition, or they may be already in fraction form. Either way, I can take these numbers and I know exactly where they go on a number line. So 2.5, I think 2.5. So that's 2.5. So I will put that right there. I just plot the point. Negative 3.75. Well, that's negative 3 and 3/4. So that's going to be between, here's negative 3.5. That's going to be halfway between negative 3.5 and negative 4. So that's going to be right about here. 4.5 is going to be 4.5 right there. And negative 1.2. Well, here's negative 1. Here's negative 1.5. Negative 1.2 is going to be a little bit closer to negative 1 than negative 1.5. So I'll go halfway, and then I'm going to move a little bit to the right. So I would say that's approximate. If I zoomed in on my number line, I could find that exact point, though, quickly. But what about pi? 3.14159, blah, 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 blah. Can I plot that on the number line? Well, I say, well, 3.14, and then it's 159. So you're going to constantly be moving back and forth. You don't know where the end of pi is, so you can't plot that point. So again, because we don't know the exact location of pi on the number line, we can't call it rational. If we knew the exact end of pi, we could, but we don't. So we can't. And there you go.